Hi dear students, in this video we are going to discuss the important theorem, that is what rank nullity theorem. Before going to the rank nullity theorem, we should know the basic definitions. So these are the basic definitions we should know before going to prove the rank nullity theorem. So range of linear transformation definition we need to know. So what is the definition of range of linear transformation? So how you are going to denote that we are going to know over here. So T is a mapping from the vector space V to W, and this T is a linear transformation. The range of T is the set of R of T, right? T of alpha, where alpha is belongs to the vector space V, is called the range of linear transformation. Or I can say that set of all T images of the elements of this vector space V is called the range of linear transformation, and we can say that this R of T is subset of W, right? So its image, T image, is in W. So set of all T images of the elements of this vector space V is range of linear transformation, right? So next definition is kernel or null space of linear transformation. So same transformation we are taking. T is a mapping from the vector space V to W, be a linear transformation. Kernel or null space, when we are going to say that this transformation, linear transformation, is kernel or null space, if T of alpha is equals to 0, the set N of T, we are denoting it as the null space or kernel of a linear transformation, we are denoting it as N of T, and that how we are going to define in the mathematical form. T of alpha is equals to 0, where alpha is belongs to V. It means its T images, elements of V. T images of elements of V in W is equals to 0, right? So where 0 is a 0 vector or 0 element of W. So clearly we can say that T of this N of T set is subset of W. So this is the definition of null space or kernel. Next we are going to move towards rank of linear transformation. So the rank of linear transformation is the dimension of the range space of T. The dimension of range space of this R of T is called the rank of linear transformation. Already we have the definition of range space, set of all what collection of T images of the elements of V is range space, or I can say that T images, right? So T images of this elements of V, set of all T images. So those T images are present in W. So when we are going to say that rank of linear transformation, dimension of that range space is called the rank of linear transformation. So next definition is nullity of linear transformation. Nullity of linear transformation means dimension of null space. Already we have discussed what is null space. So null space is denoted by N of T, and T of alpha is equals to 0 we should have, wherever alpha is belongs to V, right? So this is null space. Nullity means the dimension of null space. It's called nullity of the linear transformation and denoted as N of T. So these are the basic definitions we should know. Yes, now we'll discuss an important theorem. rank nullity theorem. Definitely there will be a question. So you should remember and you should practice this theorem. And one example they will ask. Okay. So statement. Let T is a mapping from the vector space V to W be a linear transformation and capital V be a finite dimensional vector space. Then the rank of this linear transformation plus the nullity of linear transformation is equals to dimension of the vector space V. So rank of linear transformation is dimension of R of T, right? So plus dimension of N of T is equals to dimension of the vector space V. Or I can say that rank plus nullity is equals to dimension of the vector space. Okay, domain that too. Dimension of the domain vector space. So let us see the proof of this theorem. So very easy proof. You just concentrate. We'll get to know how we need to prove. Okay. So what is our ultimate goal? We need to show that rank plus nullity is dimension of the vector space V, right? But rank and nullity, rank of linear transformation and nullity of linear transformation, definition we should do. Okay. So already we have discussed these basic definitions. Go through these definitions and remember these definitions. Okay. So very important definitions. These are very important definitions. So let suppose if I assume that V be a dimension of M, right? So the vector space V is having dimension M. That is what dimension of the vector space V is equals to M, and dimension of N of T is equals to N, right? We have taken it as small n. That is what nullity. Nullity is equals to N of T and it is N. Since N of T is a subspace of V, how it is subspace of V? See, if you observe this, T is a mapping from what? V to W we have, right? N of T, capital N of T is what? Null space, right? Null space is subspace of V, capital V, right? So N of T is a null space. Null space means T of alpha is equals to 0. Already we have discussed it. T of alpha is equals to 0. So wherever alpha is belongs to what? Alpha is belongs to capital V. So therefore obviously we can say that this capital N of T is a subset of V or subspace of V. So therefore obviously we can write down N is less than or equals to M. So this N is dimension of N of T and this capital M is dimension of V. So let us assume that capital B1 is a basis for N of T. So elements of B1 are alpha 1, alpha 2 up to alpha n, because dimension of N of T is N over here. So therefore we have taken alpha 1, alpha 2 up to alpha n be a basis of N of T, and B2 is alpha 1, alpha 2 up to alpha n and beta 1, beta 2 up to beta s be a basis of capital V we have taken. So our ultimate goal is to prove that S plus N is equals to M or N plus S is equals to M. Rank plus nullity is equals to dimension of V. Here we'll get this one is rank and this one is nullity is equals to dimension of V. S plus N is equals to M or N plus S is equals to M. Okay. So for that purpose we need to consider the transformation of the basis B1, right? So T of alpha 1, T of alpha 2, T of alpha n, T of beta 1 up to T of beta s are the elements of what? R of T, right? Range space. So R of T, but T of alpha 1 is equals to T of alpha 2 and so on is equals to T of alpha 1 is equals to 0. Why? Because according to the definition of null space, we'll get T of alpha 1, T of alpha 2, T of alpha n is equals to 0. Why? According to the definition of null space, T of alpha, every image of the elements of the vector space V is 0, right? So T of alpha, T image of alpha are 0 according to the definition of null space. So therefore T of alpha 1 is equals to T of alpha 2 and so on, T of alpha n is equals to 0. This is by definition. So therefore what I can write down, only will get these terms, T of beta 1 up to T of beta s will get. So if I consider those elements as capital S, right? So this capital S, we need to show that it is a basis of R of t. So according to the definition of basis, we should satisfy two conditions. One, we need to show that this given set capital S is a span of R of t, and this capital S is a linearly independent. We need to show that. So first step, we need to show that capital S is a span of R of t. For that purpose, we have B2 is a basis of V, right? Obviously, we have taken it. B2 is a basis of V and it spans V, obviously, right? Basis of V means obviously it spans V. So therefore, the set T of alpha 1 up to T of alpha n and T of beta 2 up to T of beta s spans R of t, right? But what we have, T of alpha 1, T of alpha 2 up to T of alpha n are 0, right? So ignore this one, only we left with T of beta 1 up to T of beta s, right? So what it means, we'll get capital S. So capital S is a span of R of t according to this one, right? So first case is over. Second case is what? S is a linearly independent. So for that purpose, we need to take the linear combination with the scalars. Suppose C1, C2 are the scalars with the set S. So set elements of S are T of beta 1, T of beta 2 and T of beta s. Okay. So we need to take the linear combination with respect to the scalars. So C1 T beta 1, C2 T beta 2 plus C3 T beta 3 plus so on Cs T beta s is equals to 0, right? So after that, if I consider transformation, if I take outside C1 B1 plus C2 B2 plus so on Cs beta s is equals to 0. T is common. So if I take outside, it is a property of transformation, right? So we need to apply the property of transformation. We'll get this one. Next, C1 B1 plus C2 B2 plus so on plus Cs beta s. Obviously, it belongs to the null space. Okay. So therefore, there exist scalars. These elements are belongs to what? N of t. Therefore, there exist scalars d1, d2 up to dn such that I can equate this term with the scalars of the means linear combination of scalars with the elements of B1's basis. Okay. So C1 beta 1 plus C2 beta 2 plus so on plus Cs beta s is equals to, I can write down d1 alpha 1 plus d2 alpha 2 so on plus dn alpha n, will get it. Obviously, in the next step we can say that d of alpha 1 plus d1 alpha 1 plus d2 alpha 2 so on dn alpha n minus c1 beta 1 minus c2 beta 2 so on minus cs beta s is equals to 0. Since this beta 2 is the basis of V, obviously already we have, so it is linearly independent. If it is basis of V, obviously it is linearly independent. But therefore what I can write down, d1 is equals to d2 and so on is equals to dn is equals to cn. Scalar quantities are equals to 0. if it is linearly independent. So therefore, obviously S is a linearly independent. So thus, what I can say that S is a basis of R of t. First step, S is a span of R of t and S is a linearly independent of R of t. Therefore, we can say that capital S is a basis of R of t. So after that, if it is basis of R of t, what is our ultimate goal? We need to show that rank plus nullity is equals to dimension of V. So therefore, what I can write down, dimension of R of t, S is a basis of R of t, right? So what is our F? Yes, capital S, T of beta 1, yes, T of beta 1, T of beta 2 up to T of beta S. How many elements are there? Up to S, small s. So therefore, dimension of R of t is what? Small s. So this is what rank of the linear transformation of t. So therefore, rank we got small s, right? This is a small s. So S plus the rank of nullity, right? Dimension of null space is n. Obviously we have taken it. So therefore, what I can write down, rank plus nullity is equals to dimension of V. Dimension of V, we have assumed that small m. So therefore, we can say that theorem is satisfies. Okay. So this is how we need to prove. It is very, very simple. According to the definition, we need to move. Okay. So let us solve some example regarding the rank nullity theorem. So they will give verify the rank nullity theorem. So you should know how we need to take the transformation and how we need to take the rank of the matrix, means rank how we need to find out, and nullity how we need to find out. Okay, all those things we need to know. So let us observe the example. Find the range, null space, rank and nullity of the linear transformation. T is V3 of R to V2 of R, defined by T of xyz is equals to y minus x, y minus z, and also verify rank nullity theorem. Okay, we need to find out first range of the linear transformation, null space of the linear transformation, and rank and nullity of the linear transformation. After that, we need to show that whether it satisfies the rank nullity theorem or not. So for that purpose, first of all, we need to know the value of range of the linear transformation, null space, rank and nullity. Okay, so let us solve this example. Now we shall write the images of elements of standard basis, right? So we have taken standard basis over here. Okay, we need to write T images. Okay, so according to the definition we need to know. Okay, if you know the definitions, then only we can simplify these examples. So we need to construct the T images. So let us see T images of standard basis. They have not given any basis over here. So therefore, first we need to take the standard basis. Transformation of 1 0 0 is equals to minus 1 0. How will get it? So how they have defined over here transformation, like that we need to take y minus x, y minus z. So here x value is 1, y value is 0 and z value is 0. So x value is 1 here, y minus x is minus 1 will get it, and y minus z is 0. So this acts as what? Alpha 1. Okay, next t of 0 1 0 will get y minus x, x value is 0, y value is 1, so 1 we got, and y minus z, y is 1, z is 0, here 1, so this acts as alpha 2. So same thing for third. Okay, so 0 minus 1 will get it, and we call it as alpha 3. So therefore R of t is transformation of what? Alpha 1, alpha 2, alpha 3. Okay, so how we need to write these terms in the matrix? Already we have discussed it. Okay, so matrix A, why we need to construct the matrix? We need to find out the rank right? For that purpose we need to construct the matrix first. Okay, so minus 1 1 0, write down like that, minus 1 1 0. Next 0 1 minus 1 0 1 minus 1. So how you are going to find out the rank of this matrix? So we need to apply the echelon form over here. Okay, so row operation or column operation you can take. So here we have taken row operation. R1 is equals to minus R1 we have taken. So minus into minus become plus 0. Minus 0 nothing but is 0 only. So 1 0. So remaining terms as it is. Next R2. R2 is what? R2 is equals to R2 minus R1 we need to take. So R2 minus R1, if I do 1 minus 1 is nothing but 0. So here we'll get 0. 1 minus 0 is nothing but 1. So here we'll get 1. And there is nothing changes in first row. Second row only we need to change. Already you know echelon form. Okay, how we need to simplify, how we need to find out the rank of matrix. Okay, so lower triangular elements should be 0. Okay, so like that we need to operate the row or column elements. So R3, if I take R3, if you observe R3 plus R2, if I do for this one R3 plus R2, so then 1 0 as it is, 0 1 as it is, only the third row will change over here. So 0 minus 1 we have. So R3 plus R2 we have. 0 plus 0 is nothing but 0. Minus 1 plus 1 will be 0. So lower triangle is 0. So this is in the form of echelon form. Therefore, if you observe the non-zero rows, non-zero rows are 2 over here. Therefore, rank of this matrix is 2. So therefore, what I can say that dimension of R of t is 2, means rank is 2. Already we got rank. Okay, so R of t is a subspace generated by 1 0 0 1, obviously, right? So therefore R of t is V2 of R. Yes, R of t how we have generated by 1 0 0 1. So therefore R of t is V2 of R. Okay, so now to find n of t, let us suppose t of xyz is 0 0, right? T of xyz is y minus x and y minus z we have 0 0. Or it is equals to what I can write down, y minus x is 0, y minus z is equals to 0. It implies x equals to y equals to z. Therefore null space is equals to, I can write down a, or directly I can write down 1 1 1. A belongs to R. Okay, so then basis of n of t are 1 1 1. Okay, so nullity means what? Dimension of null space, obviously will get 1, right? So means how many elements are there? See here, dimension 1 1 1. It is whole thing as one element. Okay, only one element we have. Therefore, dimension of nullity is 1. So rank plus nullity. Rank plus nullity. Rank already we have 2 and plus 1 is equals to 3. So dimension of V2 of R. Dimension of V2 of R. What we have? Dimension of V2 of R. See here, R of t. How we have R of t? Alpha 1, alpha 2, alpha 3. So 3. Okay. So dimension of R of t is 3. Or dimension of V2 of R, I can say that 3. Okay. So this is how we need to verify. Okay. So same thing for, yeah. Let us discuss this second example. Describe explicitly the linear transformation mapping from R square to R square such that here they have given, see here, transformation of 2 3 is equals to 4 5 and transformation of 1 0 is equals to 0 0. So we need to describe this linear transformation. Okay, so let us describe this linear transformation. Suppose if I take capital S is basis containing S is a base, so 2, 3 and 1, 0 elements of R square, okay, basis of R square. This capital S is the basis of R square and it contains 2, 3 and 1, 0. This 2, 3 and 1, 0. So for that, S is a linearly independent. If capital S is a basis of R square, it means it satisfies first condition span as well as linearly independent. So first, if I take linearly independent, suppose if I take AB belongs to R, scalar quantities, such that, so combination of scalars with these elements of the basis, so A into 2 of 3 plus B into 1 of 0 is equals to 0, 0. This one, right, is equals to 0, 0. How will get 0, 0? Right? So if I equate, S is a linearly independent, no? Linearly independent definition. Okay, this is equals to 0, 0. So if I operate this one, we'll get 2A, right? 2A plus B, first element will get. Next 3A plus B into 0 will be 0. 3A will get is equals to 0, 0. 2A plus B is equals to 0. 3A is equals to 0. Obviously A is equals to 0. B is equals to 0. See here, if I get 3A is equals to 0, it means A is equals to 0. Put A is equals to 0 over here, we'll get B is equals to 0. So therefore A is equals to 0, B is equals to 0. Therefore S is linearly independent. So now S is spans of R square we need to show. So let us say that x1, x2 belongs to R square and AB belongs to R, scalar quantities, such that this x1, x2 I can rewrite with the combination of scalars and basis of the capital S. So A into 2 of 2, 3 plus B into 1, 0. So x1, x2 is equals to 2A plus B, 3A. So this acts as what? A is equals to x2 by 3 will get, B is equals to 3x1 minus 2x2 by 3 will get. Okay, I have described over here how we'll get B value and A value. We can go through these. Okay, next, hence x1, x2 is equals to x2 by 3. In place of A, we have x2 by 3. So put that one, x2 by 3, 2, 3. Plus, in place of B, we have 3x1 minus 2x2 by 3 into 1, 0. So thus, I can say that I have, what we have done, we have eliminated A and B. Therefore, what we can say that S is a spans of R square. Therefore, S forms a basis of R square. Okay, so this is how we need to describe the linear transformation. Okay, so third example, if you observe, find the null space, range, rank and nullity of the linear transformation defined by this one. Again, you need to take a standard basis, okay, and simplify this one. It is very simple. Okay, so I will not go through this example. I have already shared the notes, so if you have any doubt you can ask free. Okay, I will stop over here.